Okay, our next speaker is Jason Heitler Klevans, who's working in UB Geary's research group at Oberlin College. His work is a collaboration between Oberlin and Case Western Reserve University. And today he'll be discussing moment-based separation of magnetic nanoparticles through the use of an inverted Halbach array.
Hi, so I'm Jason again, and I'm doing moment-based separation of magnetic nanoparticles through the use of an inverted Halbach array. I'd like to preliminarily thank my advisor, UB Geary, as well as our friends at Case Western, especially Anasemia, and our NSF grants. So, we're discussing magnetic nanoparticles. We're looking at particles that are made up of materials that in bulk are permanent magnets, but we're looking at them at a 5 to 50 nanometer scale in diameter. And when you shrink particles of this composition down to this kind of size, they end up with super paramagnetic behavior. Paramagnets are non-magnetic under normal conditions, but when you apply a magnetic field, they react linearly to the applied magnetic field. Here on the x-axis is the applied magnetic field, and as you can see, this is actually a super paramagnetic slope. You see that it has a steep slope right here. Paramagnetic materials have a not quite as steep slope, but super paramagnetic materials act like magnets much quicker, and so you can apply a very small field and have them act like magnets very quickly. This is quite a variety of biomedical applications. It's been explored, their use as contrasting agents in MRI. There's a new form of imaging, NPI. If you coat the surfaces of these particles and use an external magnetic field, you can do targeted drug delivery. And there's also the use of hyperthermia, where you put the particles onto cancer cells or tumor cells and then apply an oscillating magnetic field, heating up the particles and killing off the cancer or tumor without killing off other cells around them. Now, all these methods really require a lot of uniformity in the particles in both size and magnetic moment. So there are a variety of different methods of separation, but most of them focus on either the magnetic properties or the size properties of these particles, and few are tailored explicitly to magnetic nanoparticle separation or purification. We are investigating the use of the linear inverted Halbach array, which is a set of permanent magnets, as you can see here. And the thing of note about this is that it creates non-symmetric flux. The bottom side, which is used for a variety of different applications, has both high gradient and high magnetic field. But we're more concerned about the top side, which ends up with still high gradient but low magnetic field. And the magnetic force can be quantified as the gradient time of the moment of the nanoparticles dotted with the B field. And this also creates a uniform field along planes parallel to the surface of the array. So the main energies at work are the dipole-dipole energies between the different particles and the thermal energy. Dipole-dipole energy is expressed in this equation right here, where M is the particle magnetization, D is the particle diameter, and S is the separation between the nanoparticles. And the ratio between this dipole-dipole energy and the thermal energy indicates whether the particles are likely to chain or not. And this is very important for our separations. Now, our previous work explored separation of particles of disparate size and magnetic moment. As you can see, these particles were of 5 nanometers and 20 nanometers, and we used X-ray scattering to quantify our separation because of this size difference. This is not a particularly rigorous demonstration because of the disparity between the two sizes of particles. So we've been testing a much more stringent version where all the particles are of approximately the same size, but at varying magnetic moment. And we're also attempting to quantify the device's performance in magnetic separations. So here's our experimental setup. Our solution flows through the channel right over here and over the array. And we use vertical translation stages to raise the channel above the array And this height determines the average field and field gradient applied to the particles in our channel. Now, because of this field gradient, particles of a target magnetic moment or greater have a tendency to chain together and sink to the bottom of the channel. And then we come up with a pump rate. We estimate a pump rate to allow for the appropriate separation so that the particles that we want stay on the bottom and the particles we don't want flow through. Now, our friends over at Case Western have been synthesizing these particles for us. We use 3 compositions of composite iron oxide particles. We have, and this is based off the amount of time they've annealed, the application of heat. And FeO is actually anti-ferromagnetic, and Fe3O4 is magnetic, especially in bulk. From the relative composition of these particles, we have different amounts of magnetization. But as you can see in these TEM images, the particles are all approximately 20 nanometers in diameter. So our analysis is we use the vibrating sample magnetometer, and we fit the curve created by our data using the Langevin function, which is common in previous literature. And we assume that our magnetic moment has a log normal distribution, as shown by this equation, because of the form of synthesis, with a median magnetic moment of e to the mu and a standard deviation of sigma. So from our initial characterization, you can notice that the 4-hour annealed sample is the least magnetic, the 8-hour annealed sample is the sort of in the middle, and the 24-hour magnetic sample is the most magnetic. Here's an example of our experiment in progress. As you can see, the particles are banding in a nodal pattern corresponding to the field lines of the array, and this is for our 8-hour separation. So, as talking about our 8-hour separation, we did a preliminary run with at a very low height. We did expect some banding, and we did see that. We ran it at about 0.19 centimeters above the array, which has an average field and gradient of 95 millitesla and 81 teslas per meter. And as you can see, the distribution, which is quantified by the sigma value, remains relatively unchanged, but there was banding as we expected. So things went pretty much as we expected, and you can see that the curves are pretty similar between our original sample and our 2 trial runs. For our 24-hour sample, we ran it at a much higher height of 0.86 centimeters above the array, which has an average field and gradient of 5 millitesla and 1.1 teslas per meter. And this is because the particles are much more magnetic. As you can see from the sigma value was actually reduced from our trials. And this can be attributed to some of the most magnetic particles in the solution actually crashed out of solution. So that explains that. And again, we expected it to band, and it definitely did. For our 4-hour solution, though, we did it at the same height as our 8-hour solution, and we did not expect it to band at all because it didn't seem magnetic enough. And we used this pump rate right here. But as you can see, from this, the distribution is not reduced, but there definitely was banding. That was the important thing. We were a little confused by this, so we ran another separation at a different height of 0.35 centimeters above the array, which corresponds to 40 millitesla average field and 18 teslas per meter field gradient. And as you can see on the right, this still banded, and we expected this to not band at all. So we're not exactly sure what's going on here. But again, we did have a reduced sigma value, which indicates that we were successful in some purification of the sample. So, in summary, we did find reproducible behavior of both the 8-hour and 24-hour samples, because from our trial 1 and trial 2, those were pretty much similar. And we did find evidence of purification of the 4-hour solution, as seen by our sigma value, despite the fact that there was a disagreement between our expectations from our calculations and the actual experiment. But the array does show promise for future separations. In the future, we plan on testing, especially the 4-hour sample, to see if the certain other parameters we have can be adjusted to allow for our expectations to line up with the actual experiment. We plan on testing the flow rate, the concentration parameters, And we also plan on analyzing the VSM data, assuming different distributions of magnetic moments other than the log normal distribution. For example, we're investigating a gamma distribution or a distribution based on the small change in size between the particles. And finally, we plan on demonstrating a separation of a combination of two of the different solutions of the initial samples. Thank you.
Okay, thank you, Jason. Questions? I have a question. I'm not sure I know what you mean by a gamma distribution. Could you explain?
So a gamma distribution is simply a different distribution. It's kind of a complicated equation. So, a normal distribution is where you have, it's like a Gaussian distribution, it's just a regular bell curve. A log normal is essentially pushed to one side, and a gamma distribution is not quite a log normal distribution. It's just taking in a couple different variables. I don't have the equation up, so.
It's a modified Gaussian, basically.
Essentially.
Okay. Other questions?
I don't know if you mentioned it, but what sort of solution do you use?
We're actually using a water-based solution for these particles.
Any other questions? Okay, let's thank Jason again.